So last class we looked at what the typical IC components are available to you for design. Okay. So most probably you'll never use it in this course. At least most of it you'll never use it in this course because, for example, for your simulation projects you'll end up using, probably ideal resistors and ideal capacitors. Okay. It may be too much to expect you, but you will be using, I guess, a very detailed model of the transistor. Okay. And most probably you'll be using a 0.13 micron CMOS process for your projects. So we'll supply the models for noise, everything. It will be in one single model file. You'll just have to point to it when you run your simulations. Okay. So today we'll talk about scaling. Maybe a little bit about MOS operation. Okay, we'll see how far we can go with that. You already know your basic MOS operation, right? So your DC analysis and AC analysis and so on. But we'll look at a little bit more detail, I think, which you wouldn't have covered in the analog electronics course. Okay. So I guess, so there are two kinds of scaling. So this is, when I say scaling, I mean when you move from one process to the next. So if you have let's say if you have a 0.25 micron process, you want to go to a 0.18 micron process. Okay. So they do something called scaling. So what do you scale? You actually scale physical dimensions. You have the option of scaling physical dimensions and maybe the voltages, supply voltages, right? So there are two kinds. So one kind is actually called constant electric field scaling, and the other one is called constant voltage scaling. Okay. So what does it mean when you say constant electric field scaling? So what happens is if you scale voltage and dimensions by the same amount, your electric field will stay constant, right? So that is constant E field scaling. If you decide to keep your voltage constant and scale your dimensions, your electric field will keep increasing, right? So the danger in that is that eventually you may reach the breakdown voltage of your material, okay, of your oxide, okay. So if you see, right, look at the history of process scaling, at different points of time, they have used either constant voltage or constant E field, okay. For example, if you just plot it looks something like this, okay. So if you see, this is the process node, maybe 0.5 to maybe 0.13, okay. So let's say you plot your electric field. You'll find that before this, the voltage was somewhat constant, and they just scale the dimensions. Okay, but somewhere between 0.5 and 0.13 micron, you'll find that they've used constant electric field scaling, and then beyond that, again now they've gone back to constant voltage scaling. So what I mean is, for example, if you look at a 0.5 micron process, you'll find that, let's say the supply voltage is 5 volts. If you go to a 0.35 micron process, supply voltage would be 3.5 volts, right? If you go to a 0.25 micron process, supply voltage is 2.5 and so on, right? So till when you reach 0.13, supply voltage is around 1.3 volts. But now, after that, if you go to the latest processes like 0.65 nanometer and 45 nanometer, the voltage has stayed almost constant, okay? So it stayed almost at 1 volt. It's still at 1 volt at points for the 65 nanometer process. Okay, so we are right now doing constant voltage scaling. So let's look at you can take either one and analyze it, but let's look at the constant E field scaling, because most of the analog design, major portion of it is still done in that domain. Okay. So what are you going to do? So let's say from one process node to the other, So let's say all dimensions reduced by a factor alpha. Okay, when I say all dimensions, I mean lateral, vertical, everything. Okay. So one more thing you need to do. VDD and VT will reduce by alpha again, so that your E field stays constant. And one last thing you need to do is increase all doping levels by alpha. Okay, that you'll find that you'll also have to do that. So now let's look at the impact on different device parameters. Okay. So the first one we'll take is the current ID. So you know this is to first order, it's in saturation region. It's this. So suppose you want to look at the scaled current. So now you've scaled all the dimensions, W, L, everything. You've scaled the oxide thickness, right? What do you find? First of all, VDD becomes VDD by alpha. Okay. Okay. Actually, so VDD by alpha. Okay. So we'll also assume that means that this may not be 100% true, but we'll assume that VGS, the gate source voltage, also goes down by approximately alpha, all voltages. What happens to COX? Right? It goes as 1 by alpha. Right? Your COX actually goes as alpha times your old COX. Right? So your actual, so remember, COX is actually capacitance per unit area. So that actually increases. Right? Obviously that makes sense because your oxide thickness is actually getting smaller. Right? So your new ID prime will be this. Right? You'll find that it's actually 1 over alpha times ID. Okay, so your current levels are actually going down for a proportional overdrive. Okay. Let's look at the capacitances. What is the channel capacitance? It's W times L times COX. Right? So this goes as, obviously COX goes as alpha, W and L go as 1 over alpha. So your actual channel capacitance actually goes down, even though your COX seems to go up. And similarly, you can show that all caps tend to go as 1 over alpha times. You can look at the other capacitances, depletion capacitances, you can look at the source drain capacitances, you can look at all of them. You can analyze it a little bit further and show that they all reduce approximately as 1 over alpha times. Okay. What other parameters are we interested in? Let's take the case of GM. So it's mu COX W over L times VGS minus VT. So you'll find that GM prime stays the same. So quite often some people refer to it as constant transconductance scaling. Okay, because the transconductance in the saturation region stays the same. Is that clear? Let's look at the gate delay. Now we look at both analog and digital parameters. In this case, let's look at the gate delay. Okay. You can show that gate delay is approximately C over I times VDD. So your gate delay, so if you have an inverter or an AND gate or something like that, the gate delay for that also reduces as 1 over alpha, right? Which means effectively your process is getting faster. That's what you want. How about your power consumption? In this case, let's take the digital power consumption. So you can show that the power consumption of a digital gate is CV squared F. Okay. So your power actually goes as 1 over alpha cube, because voltage goes as 1 over alpha, capacitance goes as 1 over alpha. Frequency, you assume you're operating at the same frequency. So your power actually goes as 1 over alpha cubed. Okay, so this is obviously a major savings for you. Right? So if you want to operate for the, so you can see the advantage why people want to go for technology scaling. Right? If you go from one node to the next, you can reduce power, you can reduce your area, right? You can reduce a number of things, and you can reduce the power supply, right? A lot of things. Does anybody know what FT of a transistor is? Have you studied in the analog circuits course? Okay, so FT of the device is called the transition frequency. Okay, so this is defined as frequency at which the current gain of the transistor goes to 1. Okay. So for example, let's take a MOSFET. Don't worry about the bias for now. Okay, this is just the signal picture. Okay, so you're pumping in an input signal current, and at the output you get a signal current, right? So the point at which, so if you look at ID over IN, it stays constant for a lot of frequencies, and then eventually it starts going down. Okay, why will it start going down? You can look at it intuitively. So you actually have remember that you have a gate source capacitance here. So at very high frequencies, this gate source capacitance is actually going to be a short circuit. In other words, you're not going to get any gate source signal voltage, right? Which means your output current is going to go to 0, right? That makes sense. And of course, you can write the angular frequency also. You'll find people talking about omega t instead of ft. That's perfectly fine. Okay. And you can calculate, you can put in the capacitances and calculate it. But to do this, you're going to make a few assumptions. Okay. So some of the other capacitances you're going to neglect, like CDB, CSB, and so on. Okay, that is one. And that's a fairly straightforward assumption, because these capacitances are actually much smaller than your gate source capacitance. The other assumption you're going to make is that your gate drain capacitance, okay, which would normally matter because it's actually going from the input to the output, you're going to assume it only makes a difference for your input impedance. Okay? What is this? You can quickly analyze this and show that it's just Gm over omega times CGS plus CGD. Right? CGD, you're going to assume it only affects the input impedance. Right? You know that ID over IN equals 1 at omega t. You can use this to calculate it. Okay, your omega t of the transistor is nothing but Gm over CGS plus CGD. Is that clear? Okay. So this is obviously the maximum frequency at which the transistor can be used as an amplifier, as a current amplifier. Right? So it is actually a fairly significant parameter. And quite often, for a particular process, you can actually characterize it by its FT. Quite often you'll find people talking about, if you have a, let's say 0.13 micron process, the FT for this, obviously for a given current, the FT is of, has a certain value. Or you can get transistors with FTs of so many gigahertz. Okay? You can actually put in the expressions. So let's say first we're going to approximate this to, let's say we approximate it to Gm over CGS, because quite often CGS is maybe 10, 20 times CGD. What is CGS in the saturation region? It's 2/3 WLC ox. You remember that? Everybody remembers that? Right? So the expression for omega t is 3/2 mu n VGS minus VT over L squared. Correct? Now obviously you can also see what will happen when you scale, when you do process scaling. Right? You can see that L goes as 1 over alpha squared, VGS minus VT goes as 1 over alpha. Right? Is that clear? So obviously your omega t is actually increasing for the process, which means you can use it faster and faster, and that makes sense because what your Gm stays constant, CGS goes as 1 over alpha, right? You know that. That kind of makes sense. But this is an more explicit dependence on L, right? Because, okay, actually more explicit dependence on VGS minus VT and L, which is the overdrive and the length of the transistor. Because these are actually two design parameters, right? If you want to increase the frequency at which you are operating, how do you do it? Increase VGS minus VT. Or use the minimum length, you can. Okay? Okay, so that's it for scaling. So it's just a general overview of why you're doing. Yes. Yes. You're assuming that mobility stays constant. Okay? It is a function of the doping levels, but you're assuming that it stays more or less constant. Okay? And the place where mobility, where your doping levels play a role is in actually things like depletion capacitance, which are explicit functions of your doping levels. Okay? Here in today's class we just talked about the oxide capacitance. right, which is just a parallel plate passive capacitor, right? Once you look at, let's say, reverse bias CSB and CDB and so on, they will depend on the doping levels, right? Because your depletion region width will be a function of your doping level, and your capacitance is a function of the depletion region width, right? Okay. So now let's take a look at okay, so I won't be reviewing, since you've just done it last semester, I won't be going through, the basics of MOS operation, because I assume you're all fresh. But there are some second order effects, okay, which we will go through today. Okay, I assume you already know expressions for GM, things like that. Okay. Does everyone know what body effect is? Or backgate effect? Have you heard of that? No. Okay. Okay. So this is where the importance of the MOSFET being a 4-terminal device comes in. Okay. So normally you're used to connecting the backgate to your source. Okay, because in most cases, remember what is the bulk? Bulk is also called the backgate, by the way. Okay, and you'll see in a reason why it's called the backgate. Okay, but your bulk, remember, if you take an NMOS, what is the bulk? It's the P substrate, right? What is the P substrate connected to? The most negative potential, which is usually ground, right? And normally you're used to designing, let's say, common source or something like that. Okay, you take a common source amplifier. This is taken for granted. Right? Your bulk is connected to ground, source is also connected to ground. Correct? But in most cases, okay, you would not connect, rather your source voltage may not be ground. Okay, there are only a few cases where your source voltage is explicitly connected to ground. So what happens if your source voltage is not at ground? So what that means is it's usually at a higher potential. Your bulk always has to be connected to ground, but your source is not. So in this case, the first case, your threshold voltage. Okay, so the fundamental thing which is affected, the fundamental parameter which is affected is the threshold voltage of the device. Okay, so in the case where your bulk and source voltages are the same, the threshold voltage is called VTH or VT naught. Okay, or VTH naught or VT naught. Okay, remember the expression for this? So you have the work function, right? You remember this expression? Right? This is the expression for your for your threshold voltage. Correct? What do you find in this case? So fundamentally what happens is your depletion region width gets wider because you're effectively increasing your reverse bias voltage. Right? Look at your source, it's connected to a higher potential than your bulk. So you're basically increasing the reverse bias on your junction, and which means your depletion region width is going to get larger. Okay? That is, yes. Oh yeah, sure. You able to see now? Okay. So fundamentally your depletion region width gets larger. Okay. The other major effect is that now because your depletion region gets larger, your transistor actually cannot invert easily. Okay. Remember that the inversion charge. So remember that the gate. Okay. So the charge in the channel needs to be mirrored at the gate, right? That's when your channel actually gets slowly inverted. So now, if your depletion region width is larger, you need a larger charge to actually invert your channel, the channel region. Okay. Okay. Which means, obviously, that your threshold voltage is now no longer the same value. It's actually changing. Okay. So this is called body effect. So the new expression for threshold voltage is the old VT naught plus okay. So this is a relation of your relationship between the threshold voltage and the source bulk voltage. Okay. Obviously, when your bulk and source are connected, it's just VT naught. Okay. And again, you can all find out the expressions for phi f, right? Phi f and gamma. Gamma is this. Right? These are the expressions for phi f and gamma. This is obviously going to be process dependent, so you don't have to worry too much about, in general, you don't need to worry too much. You should know the, nature of these equations. But at least for analog circuit design, you don't need to know too much about the details, right? You need to know about the body effect. You need to know what it depends on. So those two things are extremely important. Okay. Let's take an example. I guess example in the sense. This is an example of a case you would have studied the source follower amplifier, right? You have V in at the gate and V out at the source, right? So if you look at this, your obviously in this case, your source bulk voltage, right, is an explicit function of V out, right? I mean, it is V out. In other words, your threshold voltage is an explicit function of V out. Okay? So if you're trying to get something, let's say your V in varies like this. Ideally, you expect something like this. Okay? You expect V out to just follow V in linearly, right? Except with this voltage shift, DC shift. In reality, what you'll see is something like this. Okay? Your VT starts getting larger and larger as a function of V out. Okay? We'll get to the details anyways. I mean, I think you'll understand more about this when you start analyzing circuits. There are some other second order effects. We're going to come to that actually, because now that VT is a function of your source bulk voltage, you have some other effects going on. Okay, that we're going to look at that next. But before that, I assume all of you know about channel length modulation. Everybody knows about channel length modulation, right? No? Okay. So, okay, you probably know about, you've probably used it, I'm pretty sure you've used it in the other class. You just didn't understand why it was being used. Remember that okay, remember your MOSFET characteristics? What happens if you take the slope of the current versus voltage curve here? What does it give you? What? So this is your channel length modulation. In other words, it actually gives you your GDS or G out, right? You would have studied it as lambda, you would have studied it as GDS and so on. But fundamentally the reason is because of an effect called channel length modulation. Okay? What happens is, this is your channel, right? And this is the point where the channel has pinched off. Okay? So it so happens when you change the drain source voltage, okay, the pinch off point actually moves, right? In other words, the effective length of the device actually changes. Okay? So that is what causes this G out effect, GDS, G out, RDS, whatever you want to call it. Okay? So let's say your new length is L minus delta L. For small delta L, you can write 1 over L prime as 1 over L times 1 plus delta L over L. And you can also assume that there is a relationship between delta L and your VDS. You're going to assume that's somewhat linear. Okay, so delta L over L, right? You're going to just linearize it. You're going to neglect the higher order terms. And that is where your lambda term comes from. You're just assuming it's some lambda times VDS. Okay? I'm sure you all know this relation, right? GDS is nothing but lambda times ID. Or you might, I don't know, have you studied in terms of GDS or RDS? GDS, right? Yeah. One other useful approximation is, quite often you'll see people using lambda 1 L1 as lambda 2 L2. That is, lambda L is a constant. Okay? That is also somewhat, it's a first order approximation. Okay? That is also somewhat useful when you're changing your lengths to find out your output impedance. So now we're going to look at a third effect, which is the backgate transconductance. Now you'll understand why it's called a backgate. Okay? So we looked at the effect on VT. So obviously, let's say if you just even look at your DC operating point, threshold voltage has changed. Okay? So a lot of things will change, like VGS minus VT overdrive, that will change. Right? So rather, the VGS required for a particular overdrive will change. Right? So your backgate transconductance is often represented by GMB. Okay, so this is nothing but dou ID over dou VSB. Right, now that VT is a function of VSB, as you change your bulk source voltage, you're going to change your output current, ID. Right? And of course you're going to assume that VGS and VDS are constant. That's a given. Okay, this you can write as dou ID or dou VT. Oh, sorry, dou ID or dou VT times dou VT over dou VSB, because that's the only parameter which depends on VSB. What is dou ID or dou VT? Remember that your ID is a function of VGS minus VT, right? So dou ID or dou VT is nothing but minus of dou ID over dou VGS, right? Oops. Correct? Dou ID or dou VGS is nothing but your GM of your transistor. Okay, this is minus GM of dou VT over dou VSB. Okay, you know the expression for VT, and you can differentiate that with respect to VSB, and you get this. And this is often represented as, okay, with a constant. Is that clear to everyone? So what does the negative sign mean? So fundamentally what that means is the direction of the, let's say the incremental current is actually opposite to that of your normal GM. First of all, opposite that of, right, for a given VSB. Correct? Your current direction is opposite because your current actually increases as VSB decreases. And obviously your the parameter is going to be a function of the process, so it depends on phi f and so on. Okay, normally what you'll see is it's going to be somewhere between 0.1 and 0.2, so maybe 10 to 15% is what you can expect normally. Okay, so let's say you're going to draw the small signal model. This is GDS, this is the drain, you have a bulk, okay, actually I should be careful, sorry. Okay, so typically capitalized letters stands for the DC operating point, and the small signal incremental values are represented by the lowercase letters. Okay. Okay. This is the normal direction. And you can also, to make things easier, you can actually make a small change to this, which is quite often you want to have the same direction of current for GMB and for your GM. Okay, all you have to do is write this as minus GMB times VBS and then change the direction of the current. So that is actually the most commonly used small signal model. Okay. So, and it's now called GMBS. So you know that's from bulk to source. Okay. Now, since you are changing the you're calling it GMBS, it's nothing but dou ID over dou VBS. Okay? At your quiescent point. GMBS is a positive quantity. Okay? The GMBS, once you have made all the directions correctly, GMBS will be a positive quantity, which will be in the same direction as your GM, which will typically be 10 to 15% of your GM. Okay, but it will actually depend. The small signal, voltage dependence is actually on the bulk to source. Okay. Sorry? That's because you used VSB there. Okay? That's because you use VSB there. No. If your VSB is 0, okay, what will happen is, if your VSB is 0, your VT is nothing but VT naught. Correct? So what will happen? Okay, so I understand your question. So okay, so if you set your VSB to 0, then VT is VT naught, and it will still be a function of your source to bulk voltage. If your bulk is wiggling, your source will wiggle. That's a fact. Okay, because your VT will incrementally change. Okay, so even though your threshold voltage may be the same, it does have a dependence on VSB. Okay, so your GMB will be, will be there even if your threshold voltage is, bulk and source are connected together. Okay, but it will be very, very, very small. Okay, almost 0. So the last thing we'll look at today is what is called subthreshold conduction. Have you studied this in the previous class? Probably not. Right? So far you have assumed that the transistor is, off when the current is below VT, right? And on when, the transistor is off when the VGS is less than VT, and it's on when VGS is greater than VT. Oh no, sorry, this is the quiescent point. The quiescent point is the DC operating point. Okay. So previously you would have assumed that when VGS is less than VT, the device is off. VGS goes greater than VT, your device turns on. Okay. The reality, unfortunately, is far from that. Okay. So what happens is, even that's actually a very idealized picture. As it turns out, current can flow in the transistor even if the voltage is equal to VT or even less than VT. Okay, the reason is you're assuming that the transistor goes from, gets inverted immediately, right? As you keep, right, increasing the voltage, you assume that the inversion happens instantaneously. It's actually a gradual process, right? If you keep increasing voltage incrementally, the inversion region will slowly form. Okay, so what that means is you actually have, instead of you'll have three regions. You have weak inversion, moderate inversion, and strong inversion. Okay, so the subthreshold conduction is usually refers to the weak inversion region. Okay, and there are some special characteristics about the subthreshold conduction region, which we are going to look at now. Okay. Okay, so these are the two regions we are interested in. So it turns out if you go through the analysis and find out an expression for your current as a function of the voltage in this region, right? It turns out to be something like this. Does anybody recognize this expression? Yeah, looks like a bipolar transistor actually, right? It's still a three-terminal device, so it's like a diode or a bipolar transistor, right? So it turns out that the current to voltage expression is no longer a square law, it's actually exponential. Except that in the case of you had VBE by VT for the bipolar, here you have some extra, factor, which is zeta. Okay? Of course. I'll also tell you that this is a quite approximate relation. The actual expression is a little bit bigger. It depends on your threshold voltage. It depends on your drain to source voltage. Okay, this approximate expression is valid when VDS is large. Okay, typically more than a couple of hundred millivolts. You can use this expression. The other thing is zeta happens to be greater than 1. Okay. So for the same voltage, your actual, the current and the GM and so on are lesser for a MOSFET in the subthreshold region compared to a bipolar transistor. So the bipolar zeta is actually 1. Right? And when do you have to worry about this? You have to start worrying about this when obviously when VGS or VGS minus VT becomes very small, right? So when VGS minus VT approaches, let's say your overdrive starts to approach maybe like 40-50 millivolts, your transistor most probably is in subthreshold or very close to it. Okay, remember that if you plot your inversion region, right? If this is your VT, okay, maybe around 100 millivolts around it would be your place where you're really worried about subthreshold conduction. Okay. And what does this cause? Actually, one of the things it causes is you're trying, let's say you have a digital circuit, you're trying to turn off something. Trying to turn off a bunch of gates or some huge block. You normally try to set your voltage below VT, but it turns out your current is always flowing. Even if your VGS is much less than VT, your current is still flowing in your circuit. So which means you're basically burning power even though you're turning off the circuit. So this is obviously a big problem, right? So one of the things, for example, if you have a cell phone, you're trying to turn off, all the circuits, you're not talking on it, but let's say it keeps draining your battery, right? That's an obvious big problem. Okay. Now suppose you plot, okay, ID versus VGS on a log scale. Okay, in reality you will be able to see it only on a log scale. If you try to plot ID versus VGS, it will just look like, your normal curve, right, your square law curve. Because, if you draw it on the normal thing, you won't even be able to see it. If you plot it like this, you'll see something like this. Okay. Okay, that's where you'll really be able to see the subthreshold conduction. GM is nothing but ID over zeta Vt. Bipolar is IC over Vt. Here it's less, obviously, because zeta is greater than 1. Fundamental problem. So next question is, you would have learned that bipolar transistor typically has a larger GM and so on for a given current, right, than a MOS transistor. Then the next question is, why not use this in the subthreshold region all the time? Okay. So the fundamental problem is because of FT. If you actually calculate the FT of your device, okay, it turns out to be much, much lower than your square law region. So you ideally don't want to operate it in subthreshold. Okay. So in square law, for example, for a given current, if your FT is, let's say, 10 gigahertz, if you look at the subthreshold region, your FT may only be a few hundred megahertz. Okay. And obviously you're interested in current density, because that is what will cause you to go into subthreshold. Right? If you have a very large device and you put in very little current, your VGS minus VT will be very small. Right? That is when you have a very large chance of going into subthreshold. Okay, so you have to be careful. Okay? Okay, so I guess one last thing wanted to touch upon. I assume so. You all know that. This is obvious. This should just be a refresher. But you start off, when you start analyzing a circuit, first do the DC point, right? Always start off with the DC point. To analyze the DC point, you always use the large signal characteristics, right? If it's a MOSFET, you use square law. Bipolar, you use the exponential characteristics. Okay. In the DC picture, ignore all capacitances, right? Because it's DC. So all capacitances are open circuit. Next, when you do AC analysis, then you put in the appropriate capacitances. If you have very large capacitances, they are shorts, right? And all these GM, GMBS, all of them are incremental values, right? Is that clear to everybody? I assume you should all be totally clear about this by now. Okay? Okay, so we'll stop here and continue tomorrow. And I think that's it. I won't be doing any more of MOSFETs because you already know all your incremental picture. I think all of you said you already know the capacitances, right? Of the MOSFET. You already studied the CGS, CGD and so on, the values of those in different regions of operation, right? So I won't go through that, so I'll assume all of you know it. 2/3 WLC off. So you know what the value is when it's in saturation. Okay, so you have not studied non-sat or when it's off. Okay, maybe we'll quickly go through that at the beginning of tomorrow's class. Maybe like spend 10-15 minutes on that and then we'll move on. Okay? Okay, see you tomorrow.